For decades, astronomers told us we could see about 93 billion light-years across the cosmos, the entire observable universe laid out before our telescopes like a vast cosmic map. But recent discoveries have shattered this comfortable illusion. The truth is far stranger. We've been missing most of the universe, and what we thought we knew about our cosmic horizons is fundamentally wrong. Today, we will see why the real universe might be millions of times larger than we ever imagined. And one quick question: if you could teleport anywhere in the universe for 1 hour, where would you go and what would you do? Let me know in the comments below. I will pin the most creative answer. Now let's begin. The story of our cosmic misunderstanding starts with the James Webb Space Telescope, humanity's newest eye on the universe. When Webb first opened its golden mirrors in 2022, astronomers expected to see the universe's baby pictures, small, primitive galaxies slowly growing in the cosmic dark. Instead, they found massive, mature galaxies that shouldn't exist, sitting at the very edge of time and space. These ancient giants challenged everything we thought we knew about when and how galaxies formed. But that was just the beginning of our revelations. As Webb peered deeper into space and further back in time, it revealed something that made astronomers question the fundamental assumptions about our universe. The cosmic microwave background, that faint afterglow of the Big Bang that we've mapped with exquisite precision, might not be telling us the whole story. In fact, it might be hiding far more than it reveals. Let me take you on a journey that starts 13.8 billion years ago, in the first moments after the Big Bang. The universe was smaller than an atom, hotter than anything we can imagine, and expanding faster than the speed of light. This period, called cosmic inflation, supposedly stretched space itself, carrying regions apart so quickly that light from one region could never reach another. We've always assumed this set a fundamental limit on how much of the universe we could ever observe. The observable universe, everything we can see, is limited by the speed of light and the age of the universe. Light from objects farther than about 46.5 billion light-years away hasn't had time to reach us yet. This creates what we call the cosmic horizon, beyond which we assumed was more of the same. Galaxies, stars, and empty space following the same physical laws. But what if we were wrong? What if the universe beyond our horizon is fundamentally different? Recent observations from multiple telescopes have detected what scientists call anomalies in the cosmic microwave background. These aren't just measurement errors or statistical flukes. The Planck satellite, which mapped the CMB with unprecedented precision, confirmed strange patterns that shouldn't exist if the universe is uniform beyond our cosmic horizon. There's a mysterious cold spot, an axis of evil, yes, that's what astronomers actually call it, and other features that suggest the universe might have a preferred direction or structure on scales larger than we can see. Think about what this means. Imagine you're standing in a dense forest, able to see only the trees immediately around you. You might assume the forest continues uniformly in all directions. But what if, just beyond your view, the forest gives way to mountains, oceans, or something entirely unexpected? That's the situation we find ourselves in with the universe. We've been assuming uniformity based on our limited view, but the evidence increasingly suggests we're missing something profound. The Webb telescope has photographed galaxies that appear too massive and too mature for their age. Galaxy Glass Z12, for instance, existed just 350 million years after the Big Bang, but appears as developed as galaxies billions of years older. It's like finding a fully grown oak tree in a nursery of seedlings. These discoveries force us to reconsider not just how galaxies form, but whether the universe we can see is representative of the larger cosmos. Here's where things get really wild. Some theoretical physicists now propose that our observable universe might be just one bubble in an infinite cosmic foam. This multiverse theory suggests that different regions of the greater universe might have different physical constants, different dimensions, even different laws of physics. Our cosmic horizon isn't just a limit on how far we can see, it might be the boundary between our physics and something utterly alien. The evidence for this radical idea comes from multiple sources. The fine-tuning problem, the observation that our universe's physical constants seem precisely calibrated for the existence of stars, planets, and life, makes more sense if our region is just one of countless experiments in physics. If the universe is vastly larger than we can observe, with different regions having different properties, then we naturally find ourselves in a region compatible with our existence. But the implications go even deeper. Dark energy, that mysterious force accelerating the universe's expansion, might not be uniform throughout the greater cosmos. In 2023, the Dark Energy Survey released data suggesting that dark energy's strength might vary across space and time. If true, this means the universe beyond our horizon could be expanding at different rates, creating regions of space-time that are fundamentally disconnected from our own. The cosmic web, that vast network of galaxy filaments separated by enormous voids, shows structure on the largest scales we can observe, but these structures seem to continue right up to the edge of our observable universe, suggesting they extend far beyond. Computer simulations indicate that for the patterns we see to exist, the universe must be at least hundreds of times larger than the observable portion, and possibly infinite. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has mapped over a third of the entire sky, cataloging millions of galaxies. But here's what keeps astronomers awake at night. The largest structures they've found appear to be cut off at the edge of our observable universe, like looking at a photograph where someone's face extends beyond the frame. The Hercules Corona Borealis Great Wall, a galactic superstructure spanning 10 billion light-years, seems to continue beyond what we can see. We're literally seeing partial structures that could be unimaginably larger. This brings us to one of the most profound realizations in modern cosmology. The universe we observe might be like a single room in an infinite mansion. We've been meticulously studying this room, mapping every corner, understanding how the furniture is arranged, but we've never even seen the doors leading to other rooms. And the evidence suggests this mansion might be so vast that our entire observable universe is insignificant by comparison. Speaking of feeling small in the cosmos, if this discussion about our place in the larger universe fascinates you, you'll love my other video called How Small Are We Inside the Milky Way? It explores our mind-bending position within our own galaxy and really puts into perspective just how vast space is even in our local neighborhood. Check it out after this one. I promise it'll change how you see the night sky forever. The link is in the description and on the card above. Recent data from gravitational wave detectors has added another layer to this cosmic mystery. LIGO and Virgo have detected ripples in space-time from colliding black holes billions of light-years away. But the distribution of these events hints at structures and patterns that extend beyond our observational limits. It's as if we're hearing echoes from a vast canyon, but we can only see a tiny portion of the canyon walls. The cosmic inflation theory, which explains why our universe appears so uniform, actually predicts that inflation never completely stops. In some regions of space, inflation continues eternally, creating new pocket universes constantly. This eternal inflation model suggests our observable universe is just one of countless bubbles in an ever-expanding cosmic foam. Each bubble might have different physical properties, different histories, different futures. We're not just limited in how far we can see, we're trapped in our own cosmic bubble. Here's something that will blow your mind. Mathematicians have calculated that if the universe is truly infinite, then everything that can happen must happen somewhere. There would be infinite copies of Earth, infinite versions of you, infinite variations on every possible theme. But these duplicates would be so far away, at least 10 to the 10 to the 29 meters, that we could never observe or interact with them. The observable universe becomes a tiny, unique sample of infinite possibilities. The cosmic microwave background radiation, our universe's baby picture, shows the universe at 380,000 years old, but new analysis suggests we might be interpreting it wrong. The patterns we see might not represent the entire universe at that age, but only our local region. It's like looking at a baby photo and assuming it shows the entire nursery, when it actually only shows one crib in a vast maternity ward. Dark matter, which makes up 85% of all matter, provides another clue that we're missing most of reality. We can see its gravitational effects on visible matter, but dark matter itself remains invisible. Some theories suggest dark matter might interact with itself in ways we can't detect, forming dark stars, dark planets, even dark life in regions of space we'll never observe. The universe we see might be just the visible tip of a mostly dark cosmic iceberg. The accelerating expansion of the universe means our observable horizon is actually shrinking relative to the whole. Galaxies currently visible at the edge of our observable universe are moving away so fast that their light will eventually no longer reach us. In about 100 billion years, any civilization in our galaxy will see only our local group of galaxies. The rest of the universe will have disappeared beyond the cosmic horizon. We live in a special time when we can still see evidence of the larger cosmos. But perhaps the most unsettling discovery comes from studying the universe's large-scale structure. The cosmic web shows a fractal-like pattern, with structures appearing similar at different scales. This self-similarity suggests the universe might continue these patterns far beyond what we can see. If the universe is truly fractal in nature, then what we observe might be just one scale in an infinite hierarchy of structures. Quantum mechanics adds another dimension to this mystery. The many worlds interpretation suggests that every quantum event creates parallel universes. While these wouldn't be spatially distant like regions beyond our cosmic horizon, they represent another way the total universe vastly exceeds what we can observe. Every second, countless new universes might be branching off forever beyond our ability to detect or explore. The anthropic principle, the observation that our universe seems fine-tuned for life, takes on new meaning if the universe is vastly larger than we observe. In an infinite cosmos with varying physical constants, we naturally find ourselves in a region where stars can form, chemistry works, and life can evolve. The apparent fine-tuning isn't mysterious if we're just in one of countless regions, most of which are sterile and lifeless. Recent computer simulations of cosmic evolution have revealed something disturbing. To produce the galaxy distributions we observe, the simulations require initial conditions that extend far beyond our observable universe. It's like needing to know the entire ocean's currents to explain the waves on one beach. This suggests the universe beyond our horizon isn't just more of the same. It's actively influencing what we can see through gravitational effects and dark energy dynamics. The discovery of cosmic voids, vast empty regions between galaxy filaments, provides another puzzle. The largest void we've found, the Botez supervoid, spans 330 million light-years. But statistical analysis suggests even larger voids exist beyond our observational limits. These cosmic deserts might be billions of light-years across, containing almost no matter at all. The universe's architecture might be far more varied than our limited view suggests. The most recent data from the Atacama Cosmology telescope in Chile has revealed temperature fluctuations in the cosmic microwave background that shouldn't exist according to our standard models. These anomalies suggest that gravitational influences from beyond our observable universe are affecting what we can see. It's as if we're watching shadows on a wall cast by objects we'll never directly observe. The universe beyond our cosmic horizon isn't just passively existing, it's actively shaping our observable reality through gravitational effects that transcend the limits of light-speed communication. This realization fundamentally changes how we think about cosmology. For decades, we've assumed the Copernican principle that we don't occupy a special place in the universe. But if the observable universe is just a tiny fraction of the whole, and if different regions have different properties, then our location might be special after all. Not special in the sense of being at the center, but special in having the right conditions for atoms, stars, galaxies, and life to exist. The implications for dark energy are staggering. This mysterious force, discovered through observations of distant supernovae in 1998, appears to be accelerating the universe's expansion. But what if dark energy isn't uniform throughout the greater cosmos? Recent observations from the Dark Energy Spectroscopic Instrument suggest dark energy might be evolving over time. If it varies in time, it might also vary in space, creating regions beyond our horizon where the universe's fate is entirely different from what we'll experience. And if you are enjoying this experience, make sure to subscribe to the channel and give a thumbs up. Your help means a lot to me. Now you don't want to miss out on what comes next. Consider this mind-bending possibility. Regions of the universe beyond our horizon might be contracting while ours expands. The Big Bang might not have been a unique event, but one of countless expansions and contractions happening throughout an eternal cosmos. We see expansion because we're in an expanding region, but elsewhere, universes might be collapsing, bouncing, or doing things we can't even conceptualize with our physics. The discovery of primordial black holes has added another piece to this cosmic puzzle. These black holes, formed in the universe's first second, might be far more common than we thought. But here's the kicker. If they're distributed throughout the greater cosmos, regions beyond our horizon might be dominated by black holes in ways that would make those regions uninhabitable and unrecognizable. The universe we see might be a rare pocket of relative stability in a cosmos mostly consumed by gravitational monsters. String theory, our best candidate for a theory of quantum gravity, predicts extra dimensions beyond the three spatial dimensions we experience. These extra dimensions might be compactified, rolled up too small to detect, or they might extend beyond our cosmic horizon. If extra dimensions exist, the true universe might be vastly larger in ways we can't even visualize. Our three-dimensional view might be like flatland creatures trying to understand a three-dimensional world. The holographic principle suggests something even stranger. This principle, derived from black hole physics, proposes that all the information in a volume of space can be encoded on its boundary. If true, our three-dimensional universe might be a projection from a two-dimensional surface at the cosmic horizon. But whose horizon? If the universe is larger than we can observe, we might be living in a projection from a boundary we'll never see or understand. Recent observations of quasars, the blazing hearts of ancient galaxies, have revealed alignments that shouldn't exist. The polarization of light from distant quasars shows correlations across billions of light-years, suggesting large-scale structures or forces organizing matter on scales that challenge our understanding. These alignments might be evidence of cosmic structures extending far beyond our observable universe, like seeing aligned iron filings revealing an invisible magnetic field. The cosmic neutrino background, even older than the cosmic microwave background, could tell us about the universe just 1 second after the Big Bang. But detecting these ghostly particles is incredibly difficult. When we finally map the neutrino background, it might reveal structures and patterns that extend beyond our current horizons, showing us shadows of regions we'll never directly observe. These relic neutrinos carry information from when the universe was far smaller, potentially revealing the seeds of structures larger than our entire observable cosmos. Here's a thought that challenges everything. What if consciousness itself is limited by cosmic horizons? If consciousness emerges from information processing and information can't travel faster than light, then the universe might contain islands of consciousness that can never interact. Each observable universe might develop its own conscious observers, forever isolated from others by the inexorable expansion of space. We might be just one of countless conscious regions, each asking the same questions about what lies beyond their horizons. The many interacting worlds interpretation of quantum mechanics suggests parallel universes might actually influence each other through quantum interference. While we can't observe these parallel worlds directly, their effects might be detectable in quantum experiments. If true, the universe isn't just larger than we can see spatially, it's larger across dimensions we're only beginning to understand. Every quantum measurement might be influenced by countless invisible worlds. Cosmic topology, the shape of space itself, remains one of the deepest mysteries. Our observable universe appears flat, but that only tells us about our local region. The greater cosmos might be curved, twisted, or have a topology we can't imagine. It might be like living on what appears to be a flat plane, unaware that we're actually on the surface of an enormous sphere. The universe beyond our horizon might curve back on itself or connect in ways that would seem impossible from our limited perspective. The recent detection of the cosmic gravitational wave background by pulsar timing arrays has opened a new window on the universe. These gravitational waves produced by merging supermassive black holes throughout cosmic history carry information from regions beyond our electromagnetic horizon. As we get better at detecting these space-time ripples, we might learn about cosmic structures and events far beyond what light can show us. We're developing new senses to perceive a universe vastly larger than what our eyes, or even our best telescopes, can see. The discovery of time dilation near massive objects reveals another way our view of the universe is limited. Near black holes, time slows dramatically compared to empty space. In regions of the universe with different matter densities, time itself flows at different rates. This means the universe beyond our horizon might not just be spatially distant, it might be temporally disconnected. Some regions might have experienced billions of years more evolution than others. We're not just limited by distance, we're limited by the relativity of time itself. When astronomers discovered the Great Attractor, a gravitational anomaly pulling galaxies toward it at incredible speeds, they realized massive structures beyond our direct observation influence our cosmic neighborhood. Located about 250 million light-years away, the Great Attractor is mostly hidden behind the Milky Way's disk. But even more mysteriously, the Great Attractor itself seems to be pulled by something even larger, the Shapley supercluster. These discoveries suggest a hierarchy of structures extending far beyond what we can map, each influencing the next in a cosmic chain of gravity. The Euclid Space Telescope, launched in 2023, is designed to map the geometry of the dark universe. Its early results have already surprised scientists. The distribution of dark matter appears more complex than predicted, with filaments and voids showing patterns that require structures beyond our observable universe to explain. It's like trying to understand ocean currents by looking at just one bay. The patterns we see require forces and structures far beyond our limited view. Here's something that challenges our basic assumptions. The speed of light might not be constant throughout the greater cosmos. While it's constant in our observable universe, some theories suggest it might vary in regions with different vacuum energies or dimensional structures. If true, Regions beyond our horizon might have different speed limits for information travel, creating realms where causality itself works differently. Our physics might be just local rules in a cosmos with varying fundamental constants. The cosmic web's filamentary structure shows a fascinating property called log normal distribution. This mathematical pattern appears in systems that grow through multiplicative processes over time. But for this pattern to exist at the scales we observe, the processes must have been operating over regions far larger than our observable universe. It's like finding a fractal pattern and realizing you're looking at just one tiny branch of an infinitely larger structure. Recent studies of galaxy rotation curves, the discovery that led to dark matter, have revealed something odd. The most distant galaxies we can observe seem to behave slightly differently than nearby ones. This could be due to evolution over time, but some physicists suggest it might indicate that dark matter properties vary across the cosmos. If dark matter isn't uniform throughout the greater universe, entire regions might be dominated by different forms of matter we haven't even theorized yet. The anthropic principle becomes even more profound when we consider the vastness beyond our horizon. If the universe is infinite or near infinite, then not only must life arise somewhere, but every possible form of life must exist. Silicon-based life, plasma beings in stars, conscious dark matter structures. If the physics allows it anywhere, it exists somewhere. Our carbon-based biology might be just one experiment among countless others, each in their own region of the greater cosmos. Quantum entanglement experiments have shown that particles can be correlated instantly across any distance within our observable universe. But what happens to entangled particles separated by cosmic expansion beyond the horizon? Do they remain entangled in some higher dimensional space, or does the expansion of space itself break quantum correlations? The answer might reveal whether the universe beyond our horizon is truly disconnected or linked in ways that transcend our three-dimensional understanding. The vacuum catastrophe, the enormous discrepancy between quantum field theory's prediction for vacuum energy and the observed value of dark energy, might make sense if our region is unusual. In an infinite cosmos, most regions might have the enormous vacuum energy that theory predicts, making them inhospitable to structure formation. We exist in a rare pocket where vacuum energy is anomalously low, allowing galaxies, stars, and life to form. The universe we see isn't typical, it's the exception that allows observers to exist. Black hole information paradox takes on new dimensions when we consider the greater cosmos. If information falling into black holes is preserved on their event horizons, and if black holes eventually evaporate through Hawking radiation, where does the information go? Some theories suggest it might leak into regions beyond our cosmic horizon, creating a kind of cosmic information network we can never access. The universe might be processing and storing information on scales that dwarf our observable reality. The discovery of dark flow, the mysterious motion of galaxy clusters toward a specific region of sky, suggests something massive beyond our observable universe is pulling on matter we can see. This flow affects hundreds of millions of light-years of space, all moving towards something we can't observe. It's direct evidence that the universe beyond our horizon isn't just more of the same. It contains structures massive enough to influence billions of galaxies through gravity alone. Time crystals discovered in 2016 show that matter can exist in states that repeat in time rather than space. If such exotic states of matter exist, the universe beyond our horizon might contain entire regions where time works fundamentally differently. Imagine regions where cause and effect cycle endlessly, or where time has multiple dimensions. Our linear experience of time might be just one possibility in a cosmos exploring every option. The simulation hypothesis gains new credibility when we consider cosmic horizons. If advanced civilizations can create simulated universes, and if the greater cosmos is vast enough to contain many such civilizations, then most observers might exist in simulations rather than base reality. Our cosmic horizon might not be a physical limit but a computational boundary, the edge of our particular simulation. The universe beyond might not be more space, but entirely different simulations running in parallel. The most haunting implication of our cosmic limitation comes from thermodynamics. The second law states that entropy always increases, leading eventually to the heat death of the universe. But this assumes a closed system. If the universe extends far beyond our observable horizon, our region might not be closed at all. Energy and information might flow across cosmic horizons in ways we can't detect. The fate we calculate for our observable universe, that cold, empty death trillions of years hence, might be completely wrong. Other regions might have found ways to reverse entropy that we'll never discover. Recent analysis of Type Ia supernovae, the standard candles we use to measure cosmic distances, has revealed troubling inconsistencies. These stellar explosions should have the same brightness everywhere, but subtle variations suggest the properties of space itself might change over vast distances. It's as if our cosmic rulers aren't quite standard, hinting that the universe beyond our horizon might operate under slightly different rules. We've been assuming uniformity based on local measurements, like mapping Earth's geography by studying only one continent. The lithium problem in cosmology illustrates how wrong we might be about the greater universe. Big Bang nucleosynthesis predicts 3 times more lithium-7 than we observe. This discrepancy has puzzled physicists for decades, but what if the answer lies beyond our horizon? Perhaps lithium abundance varies across the cosmos, and we happen to be in a lithium-poor region. Our failure to solve this problem using only observable universe physics might be telling us we're missing most of the picture. Cosmic rays, those high-energy particles that constantly bombard Earth, carry information from far beyond our telescopic reach. The most energetic cosmic rays have energies that shouldn't be possible. They should lose energy traveling through the cosmic microwave background, yet we detect them. This GZK paradox might indicate these particles come from exotic sources beyond our horizon or travel through dimensions that bypass our normal understanding of distance. They're messengers from realms we can't see. The axis of evil in the cosmic microwave background, a strange alignment of temperature fluctuations, might be our first glimpse of structure beyond the observable universe. This alignment shouldn't exist if the universe is random and isotropic as we assumed. Some cosmologists propose it's evidence of rotation or magnetic fields on scales larger than we can observe. Imagine living inside a slowly spinning galaxy and trying to deduce the rotation from internal observations alone. That might be our situation with the cosmos. Dark energy's nature becomes even more mysterious when we consider the greater universe. In our observable region, dark energy appears constant, the cosmological constant Einstein reluctantly added to his equations. But new observations hint it might be slowly changing. In regions beyond our horizon, dark energy might be stronger, weaker, or absent entirely. Some regions might be collapsing, while others expand exponentially. The cosmological constant might not be constant at all, just locally stable in our tiny corner of infinity. The measurement problem in quantum mechanics, why observation causes wave function collapse, might have a cosmic solution. If consciousness or observation is required for quantum collapse, and if conscious observers are scattered throughout a vast cosmos, then reality itself might be patchy. Regions with observers would have collapsed, classical physics, while regions without might remain in quantum superposition. The universe beyond our horizon might contain vast quantum realms where reality hasn't yet decided what to be. Primordial gravitational waves from cosmic inflation should create specific patterns in the cosmic microwave background. Despite decades of searching, we haven't found them. This might mean inflation happened differently than we thought, or that our observable universe is too small a sample to see the pattern. It's like looking for ocean waves by studying a bathtub. The scales are simply too different. The gravitational wave background might only be apparent on scales beyond our cosmic horizon. The possibility of variable fundamental constants becomes more plausible in a vast cosmos. The fine structure constant, which determines electromagnetic interaction strength, might vary slightly across space. If it changes beyond our horizon, chemistry itself would work differently. Regions might exist where atoms can't form stable molecules, where stars burn differently, or where the periodic table has entirely different properties. Our chemistry might be local, not universal. Cosmic voids present another mystery. These vast empty spaces between galaxy filaments can span hundreds of millions of light years, but statistical analysis suggests we should see even larger voids if the universe continues uniformly beyond our horizon. The fact that we don't might mean the universe becomes more structured at larger scales, or that some unknown physics prevents voids from growing beyond a certain size. The universe's architecture might fundamentally change at scales we can't observe. The black hole information paradox connects to cosmic horizons in profound ways. Both black hole event horizons and cosmic horizons prevent information from escaping. Some physicists propose they're fundamentally the same phenomenon viewed from different perspectives. If true, our entire observable universe might be inside a black hole in a larger cosmos, with our cosmic horizon being an event horizon from the outside perspective. We might be living inside a Russian doll of nested horizons. Recent discoveries about fast radio bursts add to the mystery. These millisecond flashes of radio waves come from billions of light years away, but their sources remain unknown. Some appear to repeat, others don't. Their distribution across the sky shows patterns that might extend beyond our observable universe. They could be signals from cosmic phase transitions, colliding dimensions, or physics we haven't imagined. Each burst might carry information about regions we'll never see. The concept of eternal inflation suggests our Big Bang was just one of countless similar events. In this model, most of space continues inflating forever, with Big Bangs creating pocket universes like bubbles in an infinite foam. Our observable universe would be just one bubble with its own beginning and eventual end, while the greater cosmos continues spawning new universes eternally. We're not witnessing the birth of the universe, just the birth of our local bubble. The discovery of wandering planets, rogue worlds ejected from their solar systems, hints at an invisible population drifting through space. Astronomers estimate there might be trillions of these dark wanderers in our galaxy alone. But here's the cosmic perspective. If such planets exist throughout the greater universe, traveling between regions with different physics, they might carry information across cosmic horizons. These lonely worlds could be messengers between realms, carrying chemical and possibly biological signatures from regions we'll never observe directly. String theory's landscape problem suddenly makes sense when we consider the vastness beyond our horizon. The theory predicts 10 to the 500 different possible vacuum states, different ways space itself could be configured. In an infinite or sufficiently large universe, all these possibilities must exist somewhere. Our observable universe, with its specific particle masses and force strengths, represents just one random valley in an unimaginably vast landscape of possibilities. We see consistency because we're trapped in one valley, unable to see the cosmic mountains and different valleys beyond. The recent crisis in cosmology, different methods of measuring the universe's expansion rate giving different results, might be our first evidence that the universe isn't uniform beyond our horizon. Local measurements using supernovae give one value, while cosmic microwave background measurements give another. This Hubble tension might indicate we're in a cosmic bubble with slightly different properties than the greater universe. It's like measuring Earth's curvature from one small region and assuming the entire planet has that same curvature. Gamma-ray bursts, the most energetic explosion since the Big Bang, show peculiar patterns in their distribution. These cosmic fireworks, lasting from milliseconds to minutes, release more energy than our Sun will produce in its entire lifetime. But they seem to avoid certain regions of sky and cluster in others. This anisotropy might reflect structures extending beyond our observable universe, like seeing lightning patterns that reveal the shape of unseen storm systems. The concept of time becomes even stranger when we consider the greater cosmos. In our observable universe, time flows from the Big Bang toward heat-death, but in regions beyond our horizon, time's arrow might point differently. Some regions might experience time backward from our perspective, with entropy decreasing and complexity spontaneously arising. The second law of thermodynamics might be local, not universal. What we call the past might be another region's future. Dark matter's true nature might only be understandable in the context of the greater universe. The 5-to-1 ratio of dark to ordinary matter in our observable universe might be unusual. Other regions might be dark matter dominated or entirely lacking in dark matter. If dark matter comes in many varieties, a whole periodic table of dark elements, different regions, might have different dark chemistry. Our inability to detect dark matter directly might stem from looking for the wrong thing based on our local sample. The quantum Zeno effect, where frequent observation prevents quantum systems from evolving, might operate on cosmic scales. If conscious observers affect reality through quantum mechanics, then regions of the universe with many observers might evolve differently than empty regions. The greater cosmos might be a patchwork of different realities, each shaped by the presence or absence of observation. Our observable universe's properties might reflect the accumulated effect of billions of years of observation by countless conscious beings. Recent discoveries of ultra-diffuse galaxies challenge our understanding of galaxy formation. These ghostly galaxies have the mass of typical galaxies but spread over areas 10 times larger, making them nearly invisible. They shouldn't exist according to our models, yet we keep finding more. They might be evidence of different formation mechanisms operating beyond our cosmic horizon, or remnants of interactions with structures we can't see. Each anomalous galaxy is a clue that our local physics might not be the whole story. The cosmic coincidence problem, why dark energy and matter density are comparable right now when they evolve differently over time, suggests we're missing something fundamental. In our observable universe, we happen to live at the moment when these densities are similar, but this might not be a coincidence if the greater universe has regions in different phases. We might be in a transition zone between matter-dominated and dark, energy-dominated regions, explaining why we see rough equality. Magnetic fields in the universe show coherence over impossibly large scales. Galaxies billions of light-years apart have magnetic fields that seem correlated. These correlations can't be explained by any known mechanism operating within our observable universe. They might be fossils from a time when these regions were connected, or evidence of physics operating beyond our cosmic horizon. The universe might be threaded with magnetic connections we can only glimpse. The discovery that galaxy clusters move in bulk flows challenges the cosmological principle of large-scale uniformity. These flows, involving thousands of galaxies moving together, suggest gravitational influences from beyond our observable universe. It's as if we're seeing just one part of a vast cosmic river system, trying to understand the flow without seeing the source or destination. The universe in motion reveals forces beyond our vision. Quasar absorption lines tell stories of intergalactic gas clouds billions of years old. But some absorption patterns don't match any known element or molecule. These mystery lines might come from exotic matter created in regions with different physics. As light travels billions of years to reach us, it passes through regions that might harbor forms of matter impossible in our local universe. Each spectrum is a core sample through space-time, revealing layers of cosmic history and geography. The topology of space itself remains unknown beyond our observable universe. While our local region appears flat, the greater cosmos might be curved, twisted, or have holes like a cosmic Swiss cheese. Advanced civilizations in different regions might have mapped these features, using them for navigation or communication in ways we can't imagine. Our flat patch might be like assuming Earth is flat because your backyard is level. Consciousness itself might be limited by cosmic horizons in ways that affect the nature of reality. If consciousness plays a role in quantum collapse, and if conscious observers are scattered throughout a vast cosmos, then reality might be fundamentally different in regions with different densities of observers. The observable universe might have the properties it does because it's been shaped by billions of years of observation, while unobserved regions remain in primordial quantum states. The James Webb Space Telescope's discovery of impossibly massive early galaxies has forced a complete revision of our cosmic timeline. Galaxy JD's GS Z14-0, observed as it was just 290 million years after the Big Bang, contains hundreds of millions of stars that shouldn't have had time to form. But what if these galaxies aren't anomalies? What if they're evidence that our region of the universe had different initial conditions than we assumed? The greater cosmos might contain regions where galaxy formation happened faster, slower, or not at all. Recent neutrino telescope observations have detected particles with energies that challenge our understanding of cosmic accelerators. The ice cube detector in Antarctica has recorded neutrinos carrying more energy than any known process should produce. These ghost particles, which barely interact with matter, might be carrying messages from regions where physics operates at energy scales we've never imagined. Each ultra-high energy neutrino is a postcard from realms beyond our cosmic horizon. The sterile neutrino problem adds another layer to our cosmic ignorance. Experiments hint at a fourth type of neutrino that doesn't interact through any known force except gravity. If sterile neutrinos exist, they might dominate regions of the universe beyond our horizon, creating vast dark sectors we can never directly observe. Our three-neutrino universe might be unusual, a small island of interacting matter in an ocean of sterile darkness. Here's a disturbing possibility. The universe might be infinite in spatial extent but finite in the configurations of matter it can contain. This means that somewhere beyond our cosmic horizon, exact duplicates of our observable universe must exist. Not similar regions, but atom-for-atom copies, including copies of Earth, you, and everyone you know. The distance to the nearest copy can be calculated, about 10 to the 10 to the 115 meters. This isn't science fiction, it's the logical consequence of infinite space with finite possibilities. The cosmic web's filamentary structure shows properties of a neural network. Galaxies cluster along filaments, with nodes where filaments meet containing massive galaxy clusters. This pattern resembles neurons and synapses in a brain. Some researchers have found mathematical similarities between the universe's large-scale structure and biological neural networks. If this pattern continues beyond our horizon, the universe might possess a kind of structure that processes information on unimaginable scales. Dark energy's equation of state parameter, W, determines the universe's ultimate fate. In our observable universe, W appears to be close to -1, indicating constant dark energy. But tiny deviations from -1 would dramatically change the universe's evolution. Regions beyond our horizon with slightly different W values might be experiencing big rips, big crunches, or cyclic expansions and contractions. Our stable expansion might be a local anomaly in a cosmos exploring every possible ending. The missing baryon problem, ordinary matter that should exist but can't be found, might have a simple solution. It's beyond our horizon. Big Bang nucleosynthesis tells us how much ordinary matter should exist, but observations find only about half. Recent discoveries of warm-hot intergalactic medium account for some missing baryons, but not all. The rest might be in structures too large to fit within our observable universe, like trying to weigh an elephant by examining 1 foot. Quantum field theory predicts that empty space should weigh 10 to the 120 times more than observed. This vacuum catastrophe might be resolved if our region is extraordinarily unusual. In the greater cosmos, most regions might have the enormous vacuum energy that theory predicts, making them uninhabitable. We exist in a rare bubble where quantum fluctuations nearly cancel out, allowing structure formation. The universe we observe is the exception, not the rule. The axis of evil in the cosmic microwave background aligns suspiciously with our solar system's orientation. This alignment could be a bizarre coincidence, an error in data analysis, or evidence that our local motion through a larger structure affects what we observe. If the latter, it means the cosmic microwave background isn't purely showing us the early universe. It's showing us how we're moving through something much larger than our observable cosmos. Primordial black holes from the universe's first second might bridge regions with different physics. These ancient black holes, smaller than atoms but more massive than mountains, could carry information about the universe's initial conditions. If they formed from quantum fluctuations during inflation, their properties might vary across the greater cosmos. Some regions might be dominated by primordial black holes, creating a dark universe we can barely imagine. The multiverse interpretation of quantum mechanics suggests every quantum event branches reality. But these branches might not be separate universes, they might be different regions of the same vast cosmos. Quantum decoherence would prevent regions from interfering, making them effectively separate worlds. The universe beyond our horizon might contain all possible quantum histories, each evolved into its own region of space. Type 3 civilizations on the Kardashev scale would harness energy from entire galaxies. If such civilizations exist beyond our cosmic horizon, they might be engaged in cosmic engineering projects that reshape space itself. They could be creating baby universes, manipulating dark energy, or building structures from exotic matter. Our apparent isolation might be artificial, a kind of cosmic nature preserve maintained by intelligences operating on scales we can't perceive. The holographic principle suggests our three-dimensional universe might be encoded on a two-dimensional surface. But which surface? If the universe is larger than we observe, multiple holographic screens might exist, each encoding different regions. Reality itself might be layered like an onion, with each layer representing a different holographic projection. We see one layer unaware of the others. Recent observations of galaxy cluster collisions reveal that dark matter behaves differently than expected. In some collisions, dark matter appears to self-interact, while in others, it doesn't. This inconsistency might indicate different types of dark matter in different regions, or dark matter that behaves differently under conditions we don't fully understand. The dark sector might be as complex as the visible sector, with its own periodic table of elements we haven't discovered. The fine-tuning of physical constants becomes less mysterious if constants vary across the greater cosmos. The strength of forces, particle masses, and space's dimensionality might all vary beyond our horizon, Anthropic selection ensures we find ourselves where conditions allow atoms, stars, and life. But this raises profound questions. Are there regions where consciousness takes forms we can't imagine, where information processes through structures other than matter? The discovery of time, loops in general relativity, opens terrifying possibilities for regions beyond our horizon. While our observable universe seems to forbid closed time-like curves, the equations don't prohibit them everywhere. In regions with extreme space-time curvature or exotic matter, cause and effect might form loops. Entire sectors of the greater cosmos might exist in temporal bubbles where history repeats endlessly or where future events cause past conditions. Our linear time might be unusual, a small island of causality in an ocean of temporal chaos. Recent analysis of the cosmic microwave background by the Planck satellite revealed something called hemispherical asymmetry. One half of the sky shows slightly different properties than the other, as if the universe has a preferred direction. This cosmic yin-yang shouldn't exist if the universe is uniform and isotropic. It might be our first glimpse of a gradient extending beyond our horizon, evidence that we're on the slope of some cosmic mountain whose peak lies forever beyond our view. The lithium problem has deepened with better measurements. Not only is there 3 times less lithium-7 than Big Bang nucleosynthesis predicts, but lithium-6 is 10,000 times more abundant than it should be. These discrepancies might indicate that nuclear physics worked differently in parts of the early universe, or that our region experienced unique conditions. The periodic table itself might vary across the cosmos, with different regions having different elemental abundances and nuclear stability. Dark flow, the mysterious motion of galaxy clusters toward a specific region of sky, affects at least 1,000 galaxy clusters across billions of light-years. The motion is coherent, as if something massive beyond our horizon is pulling on matter we can see. NASA's studies suggest this flow extends to at least 2.5 billion light-years, but it might continue much farther. We're seeing the gravitational shadow of structures that might dwarf anything in our observable universe. The quantum vacuum isn't empty, but seethes with virtual particles popping in and out of existence. This vacuum energy should be enormous, yet we observe almost none. What if vacuum energy varies across the cosmos like altitude on Earth? We might live in a rare valley where vacuum energy is near zero, while most of the universe exists on high plateaus of enormous vacuum energy, where particles can't form stable atoms. Our existence depends on winning a cosmic lottery we didn't know we were playing. Observations of distant supernovae show they're fainter than expected, revealing the universe's accelerating expansion. But subtle variations in supernova brightness might indicate that acceleration isn't uniform. Some regions might be accelerating faster, others slower, creating a cosmic patchwork of different expansion rates. If acceleration varies in space, the greater cosmos might contain regions racing away so fast they've already reached the Big Rip, while others remain nearly static. The missing satellites problem reveals our models are incomplete. Simulations predict thousands of small galaxies should orbit the Milky Way, but we see only dozens. Either dark matter behaves differently than we thought, or something prevents small galaxies from forming. That something might be influences from beyond our cosmic horizon, gravitational tides from structures we can't see, or variations in dark matter properties that change how galaxies assemble. Cosmic rays above the GZK cutoff energy shouldn't exist. These particles carry so much energy they should lose it to interactions with the cosmic microwave background within 50 million light-years. Yet we detect them regularly. They might come from exotic sources beyond our horizon where physics allows higher energies or travel through extra dimensions that bypass the distance limit. Each impossible cosmic ray is evidence that our understanding of the universe is fundamentally incomplete. The measurement of space-time foam at the smallest scales suggests space itself might have different properties beyond our horizon. Quantum gravity effects should make space-time fuzzy at the Planck scale, 10 to the negative 35 meters. This fuzziness might vary with vacuum energy or other factors. Regions with different quantum foam properties would have different limits on measurement, computation, and perhaps consciousness itself. Recent discoveries of supervoids challenge our understanding of structure formation. The Bootes supervoid spans 330 million light-years, so empty that light crossing it arrives cooler than expected. But statistical analysis suggests even larger voids should exist if the universe continues uniformly. Their absence might mean the universe becomes more structured at larger scales, or that unknown physics prevents voids from growing beyond certain sizes. The entanglement of space itself suggested by quantum gravity theories means the universe might be fundamentally non-local. Points that seem distant might be connected through quantum entanglement in higher dimensions. The greater cosmos might be a vast quantum network where information flows through channels we can't perceive. Our classical, local view of space might be an approximation that breaks down beyond our cosmic horizon. Black hole complementarity suggests information can exist in multiple places simultaneously, both inside a black hole and encoded on its surface. If cosmic horizons work similarly, information about regions beyond our horizon might be encoded on the cosmic microwave background. We might already have access to information about the greater universe, encoded in patterns we don't yet know how to read. The discovery of gravitational wave memory effects shows that passing waves permanently distort space-time. Over cosmic time, countless gravitational waves from beyond our horizon have passed through our region, each leaving subtle distortions. Space itself carries scars from events we'll never observe. By reading these gravitational memories, we might learn about the universe beyond our direct observation. Recent studies of cosmic topology using the cosmic microwave background have tested whether space curves back on itself. While we've ruled out small-scale curvature, the universe might still have topology on scales larger than we can observe. We might live in a cosmic Klein bottle or on the surface of a four-dimensional torus. The apparent infinity of space might be an illusion created by light circling a finite but boundless cosmos. The emergence of complexity shows fascinating patterns across scales. From subatomic particles to galaxy clusters, nature builds complex structures through simple rules. But our observable universe might be too small to see the largest scales of organization. Beyond our horizon, structures might exist that make galaxies' superclusters look like atoms, vast patterns of organization operating by rules we haven't discovered, creating forms of complexity we can't imagine. The crisis in understanding dark matter has reached a breaking point. Every experiment designed to detect dark matter particles has failed. The Large Hadron Collider found no supersymmetric particles. Underground detectors see no WIMPs. What if we're looking for something that doesn't exist in our region? Dark matter might take completely different forms beyond our cosmic horizon. Dark atoms, dark chemistry, even dark life. Our 5-to-1 ratio of dark to ordinary matter might be unusual. Other regions might be entirely dark, with ordinary matter as the exception. Astronomers recently discovered that ancient quasars, billions of light-years away, show no time dilation in their flickering. According to relativity, distant objects should appear to evolve in slow motion due to cosmic expansion. But these quasars flicker at the same rate as nearby ones. This paradox might indicate that our understanding of cosmic expansion is incomplete, or that space-time itself has properties that change over cosmic distances. The universe beyond our horizon might not be expanding at all, or expanding in ways that violate our extrapolations. The cosmic neutrino background, relic particles from when the universe was 1 second old, carries information we're only beginning to decode. These neutrinos decoupled from matter when the universe was far smaller, potentially carrying imprints of structures that now lie beyond our horizon. When we finally map this neutrino background precisely, we might see shadows of regions that have been causally disconnected from us since the first second of time. Here's a possibility that reshapes everything. Consciousness might be fundamental to physics, not emergent from it. If conscious observation causes quantum wave function collapse, then regions of the universe without observers might remain in permanent superposition. The greater cosmos might contain vast quantum realms where reality hasn't decided what to be. Our classical universe might exist only because it's been observed, while unobserved regions remain in primordial quantum indefiniteness. The discovery of ultramassive black holes in the early universe challenges our models of growth. These monsters, billions of times our sun's mass, existed when the universe was less than 1 billion years old. They couldn't have grown that large that fast through known mechanisms, unless our region experienced unique conditions, or unless black holes can grow through processes we haven't discovered. The greater cosmos might contain black holes so massive they defy our concepts of space and structure. Magnetic monopoles, particles with only north or south magnetic poles, should have been created in the early universe, yet we've never found one. Their absence is so puzzling it's called the monopole problem. But what if monopoles dominate regions beyond our horizon? Different cosmic regions might have frozen out different particles during phase transitions. Our monopole-free zone might be unusual, allowing the electromagnetic phenomena that make our chemistry possible. The quantum Darwinism hypothesis suggests that classical reality emerges through a selection process where certain quantum states survive environmental decoherence. But this process might work differently in regions with different environments. Beyond our horizon, different selection pressures might create different classical realities from the same quantum foundations. Reality itself might evolve differently across the cosmos. Recent observations show that fundamental constants might vary over time and space. The fine structure constant, determining electromagnetic interaction strength, shows hints of variation in distant galaxies. If confirmed, this means the greater cosmos might contain regions where atoms can't form, where chemistry works differently, or where electromagnetic forces dominate gravity. Our stable constants might be a local phenomenon, like weather on a cosmic scale. The existence of great attractors and dark flows suggests the observable universe is like a small boat on a vast ocean, pulled by currents and tides we can't see. The Shapley supercluster, 500 million light-years away, pulls thousands of galaxies, including our own. But Shapley itself moves towards something even larger. We're seeing the local effects of a gravitational hierarchy that might extend infinitely beyond our vision. Cosmic voids grow over time as gravity pulls matter into filaments and walls, but the largest voids we observe seem to have stopped growing, as if they've reached some maximum size. This might indicate unknown physics that prevents voids from expanding indefinitely, or influences from beyond our horizon that stabilize large-scale structure. The architecture of the cosmos might be regulated by forces we haven't discovered. The information paradox extends beyond black holes to cosmology itself. If information can't be destroyed, where is the information from regions that have passed beyond our cosmic horizon due to expansion? It might be encoded in subtle correlations in the cosmic microwave background, in the distribution of galaxies, or in quantum entanglement patterns we haven't learned to read. The observable universe might be a hologram containing information about regions we can no longer see. Time crystals demonstrate that matter can exist in states that repeat in time rather than space. If such exotic states exist, the greater cosmos might contain regions where time itself is crystallized. where events repeat in perfect cycles, where causality forms loops where past and future lose meaning. Our linear time might be unusual, a melted region in a cosmos of frozen temporal patterns. The simulation hypothesis gains credibility when considering cosmic horizons. If reality is computed, cosmic horizons might be rendering boundaries, limits on what needs to be simulated in detail. The universe beyond might not exist until observed, like a video game that only renders what the player can see. Our investigations of the cosmic horizon might be pushing against the computational limits of reality itself. Recent discoveries of planets in impossible orbits, hot Jupiters, super-Earths, rogue planets, show that planetary system formation is far more varied than we imagined. If such diversity exists just within our observable universe, imagine the exotic arrangements beyond our horizon. There might be regions dominated by rogue planets, binary planet systems, or configurations we haven't conceived. The cosmos might be experimenting with every possible arrangement of matter. The vacuum birefringence predicted by quantum electrodynamics was recently confirmed near neutron stars. Empty space itself becomes polarized in extreme magnetic fields, splitting light like a prism. In regions beyond our horizon with different vacuum properties or extreme fields, light itself might behave in ways we've never observed. There might be dark regions where photons can't propagate, or brilliant regions where vacuum energy creates light from nothing. If you are still watching, I am sure you will love this other video at the left side of the screen. This is why we can't leave the Milky Way. In this video, discover the real science and cosmic barriers that make intergalactic travel impossible, not just for us, but for any civilization. See you there.